mij krijg je wat extra tijd om de weg hier naartoe te vinden.
Hi, good evening everyone. Welcome here to the Eindhoven Innovation Café. Nice to see you all again and new faces. Hi to everyone watching online as well. For those who haven't been here before, we are a weekly networking event where we offer presentations on the subjects of design and or technology. Tonight we have Jeroen Sol here talking about 4D printing and all of its possibilities. And afterwards we'll have the opportunity for drinks and dinner, just as usual. There is an event happening which will have to be tidied up, so we're going to have to see how we'll do it, but it's all going to be possible. But I'll walk you through it later. But first, enjoy the presentation.
Yeah, thank you. Thanks for the introduction. Yeah, I'll try to walk you through this topic, 4D printing. You can maybe tell from her hesitation with like 4D printing that it could be a bit nebulous, but I'll try to clarify all of that. And I'll talk about 4D printing based on these objects that you see here. I had this lovely gentleman in the audience already tell me that they look like insects, which was a very good thing that he observed there. And well, it's besides 4D printing also a story about what chemistry can do and where we find inspiration for the research that we do and innovations that we make. In case you missed it in October, this was at Dutch Design Week, where I demonstrated the beetles that you saw in the previous slide as well. And these are no ordinary beetles. They are 3D printed, yes. But the fourth dimension that I was alluding to is a change in time that they can undergo or do. And that's a change that doesn't happen spontaneously, but that's something that we actively made happen, that we programmed into the materials. Because what happens to these, I hope none of you are colorblind, but you can see these green beetles. If we then humidify the container that they're placed in, there we go, they will turn red as they undergo like a water-induced color change. Then if the air dries again, they turn back green, and we can cycle this again. They will turn red a second time, and then they will dry again. So it's a cyclical behavior that we can cause here, where these beetles change their color in response to water. And that's a couple of things come together, which is chemistry, design of materials, and also, well, of course, these beetles. That sort of are made to captivate the audience. But it all starts with me, of course. That's the slide I briefly showed. This is me, Jeroen Sol, as was already noted. And this is me at the printing machine where we make these. It also gives you an idea of the scale of these beetles. They're about, well, half a finger's length or so. And they consist, in this case, of two materials, this black material that was printed and then this green material, the smart material that was printed on top. Now, why was I so well suited to tackle this 4D printing topic? Well, it requires a bit of look inside my head and what makes me tick. And if you look inside my head, you will find this, well, quite literally, but also a bit metaphorically, that I tend to tackle problems that I see by thinking about the molecules that are at play. What happens to the molecules? Do they cause a problem? Can they be used to fix a problem? Can I make molecules or think of molecules that can fix issues? And sort of with this in mind, I worked for about 4 years on the future of 3D printing, but specifically towards new materials development, responsive materials to make responsive devices, which we then call 4-dimensional printing instead of 3-dimensional. The devices that were developed by me and my colleagues can change shape or color in response to a change in their environment, and that can be humidity or specific types of light irradiation or temperature. That all sort of fits within this banner of 4-dimensional printing. This is conventional 3D printing that you might have at some point seen in your lives as well. It generates static objects. It's a useful technique if you want to very quickly transform a computer model into a physical object. But it's not very well suited for mass production or well, making very functional things. It's mostly used as a prototyping tool or for one-offs. So to change this from 3D printing into 4D printing, we need to sort of rethink the materials, because the technology by itself is great. That provides a lot of room for opportunities, but the materials that we use are simply not suited for, let's say, extra functionalities. So to move beyond conventional 3D printing, we need to change the materials. We need to develop new ones. And like many material scientists, I take inspiration from nature, because nature has had, I don't know, about a couple billion years to sort these things out. Maybe it wasn't always very structured in the way that nature innovated, but there's a lot of different solutions that nature has found to very disparate problems. And that's where I tend to find a lot of inspiration with my sort of combining my chemical knowledge and this inspiration. So it all traces back to this specific beetle. That's its Latin name. I'm not going to try and tackle that. It's one that lives in Indonesia, and it's also, well, a similar size to the 3D printed ones, so about half a finger's length. And for some reason, I don't really know why, it has this beautiful green sort of outer shell, which changes color in response to water. So the beetle becomes red when it's wet, and then when it dries out, it becomes green. As I said, I don't really know why it does this. I just know it does do that. And that provides a very well, interesting example for me of like a function that nature does that we can maybe use, copy, and then improve upon sort of towards the future. And this is then also obviously what I based the artificial beetle on. Now you maybe see the resemblance between the two. Ours also starts at green and then becomes red when it becomes wet. So we have our conventional 3D printing technique that we at this point know pretty well, especially as chemists and material scientists. It's something that we see more often. And we have these 4D printed beetles, but there's some crucial steps in between that I want to go over with you. Like, how do we get from the conventional 3D printing that I sort of gave a bit of shade just now, and how do we get to 4-dimensional printing with these responsive beetles that change color. And this actually, in my case, it's a combination of a bit of Eindhoven history and a lot of chemistry. In some way, it all traces back to the 1980s and Philips. Philips, of course, the company that made Eindhoven what it is at the moment. Not necessarily a topic they were working on that's sort of directly related, but what they were doing is working on fiber optic cables, so these glass fiber cables for telecommunications. And a very specific problem they were facing is that the outside shell of that fiber optic cable needs very specific properties, because otherwise it will break the fiber if it gets too warm or too cold. And they were looking for well, in a very similar way, essentially as I am doing, they were looking at this problem from a chemical viewpoint. They had the problem they saw, we need to make a good cladding, and they started looking for molecules that they could use for this to get the desired properties. And the material that they developed, it's a molecule that has a very specific shape, and I can imagine not all of you are chemists in the way that I am, but there's like one specific thing you need to take away is that the molecule looks like this. I guess to some of you it could be pretty much any other molecule, but what you need to remember is that there is sort of this oval shape. Maybe if you squint your eyes a bit, you will see that this molecule also has somewhat of a sort of a lengthened shape. It's a bit sort of maybe like this pointer if you look at it. And that's the main takeaway that you need to remember. The molecule has a sort of this elongated shape. What makes that special is that this molecule, when it is in the right temperature range, it tends to self-organize. This is, the basis of this is a lot of physics. But what happens is that these molecules, they work best if they all align in the same direction. And this was then for Philips one of the solutions that they needed that if they cladded their fiber optic with these molecules, the molecules would all be in a single direction, and this would give them specific properties that they were looking for. So we have this molecule. This is just a molecule. We call this a liquid crystal. That name might ring a bell. This is a liquid crystal, and these liquid crystals, at the right temperature, they'll organize into this sort of very nicely aligned state. A bit later, this is something else you might know Philips for, is the liquid crystal display. Liquid crystal again. Philips did not actually develop sort of the main body of the TV, but there are specific optical layers in there that they optimized towards sort of mass market optimization. You can also see from this photo, it's one I sort of plucked from the internet, there's a big difference in the different viewing angles from the TV. This one's quite dim, this one's extremely bright in comparison. That's the thing that Philips tackled, and they realized they could tackle this with the same liquid crystal, so this elongated molecule. So Philips, clearly has a long history with these molecules, first from fiber optics, then they made LCD televisions more appealing, and it might well be that this television has a layer that was originally, or at least some predecessor of it was originally developed at Philips using the same molecules. Now, taking a couple steps forward, so we're moving about 30 years forward in time. What I'm going to show you is an artificial muscle, so a muscle that's designed and made by humans. That was also 3D printed by the group of Jennifer Lewis, that's a professor in America at Harvard, who also does a lot of 3D printing research. And together with a lot of other researchers, they realized that these liquid crystals could find yet another use. So besides fiber optic cables and televisions, they could 3D print them. So again, the same molecule as that's in most people's television. They made this device, and I think it needs a while to load. There you go. It's a small plastic strip that is, it's a bit rubbery. It's a bit like a rubber band that you might use at home as well. And this is essentially a hairdryer. It expels hot air. And what you then see is that when it gets warm, this thing contracts and it sort of pulls up this weight. Of course, the name artificial muscle was chosen to exert some inspiration from nature to show that it was inspired by nature. But that's, I guess the name that sells in the end, this being an artificial muscle. And this is also something that the research group at TU Eindhoven that I was a part of also worked on. But not specifically what I was doing. I was looking for something else that I could 4D print. Not the artificial muscle, but something with a bit more color, something a bit more intriguing to me. And again, going back to nature, I found this in this beetle. So this is a different beetle, a scarab. And the scarab has a very bright color, you might know it, this bright green. At least for this one. And the intriguing thing with this one is that its color does not come from a pigment, so it's not like the stuff that's in nail polish, for instance, or hair dye. There's no colorant in here, but it's a physical effect that's down to the molecular structure. And this might be a bit abstract, but what you need to potentially remember here is if we would cut open its shell and use a very fine microscope, this is what we would see, a layered structure. That's 300 nanometers, that's extremely small. So if this is a centimeter, that's about 30,000 times as small. So this is a very fine structure. And what's also important, but that's even more abstract, is that this structure is helical. So there is also an orientation in the molecules in these layers, and they form sort of a spiral pattern. And that causes this color to emerge. So there's no pigment in there, no colorant, but it's just purely a physical effect of these molecules being arranged in a specific way, the light then coming in and then getting reflected off or not reflected off. Well, that gave us a nice opportunity because we have these liquid crystals that I mentioned before. They all align, in this case, in what we call a uniaxial way, so they align along a single direction. But there is what I tend to consider sort of a magical molecule that we call a chiral dopant. And this chiral dopant induces exactly this type of alignment. So we get sort of the spiral alignment in our liquid crystals. We can tune this a little bit depending on the amount of this Carl dopant magic molecule that we add. And then this the period with which this spiral happened is about the same length scale as this one. Which means that from a material that is typically transparent, I mean, look at this television, it clearly is transparent. By adding this chiral dopant, we now have a material that is brightly colored, even without us adding any pigments or colorants. So it's clearly a physical effect that's driving this. And because it's a physical effect, that leaves us a lot of room to play around with that, essentially. Of course, being chemists, going back to the chemistry again, the material I showed you just before, this colored square, that cannot be 3D printed. That was designed sort of industrial processing into big televisions like this. That's not usable for 3D printing. So to do that, we need to do some chemistry. I see the video is not playing, but assume there's this hot boiling sort of mass in the flask over there. We put our liquid crystals in there with some other molecules that make it suitable for 3D printing. It boils for a while, it stirs, takes about an hour. And then what comes out is material that looks like this. It might be a bit hard to see, but you see it at the rim of this vial, the inside as well, that we see the emergence of color. And that is without adding any dye or colorant. This material by itself, as you can see from the reaction, there's no color, it's colorless. But then when it sets, color emerges and we get our suitable material. So this material is colored and, very important, it's also quite sticky. So if I had to describe the consistency of it, it would be, I guess, Nutella or peanut butter. That's sort of what you have to look for. But then peanut butter with a very bright color, a very nice color, if I might add. And this is then ready for 3D printing. That printing happens what we call a micro extrusion machine. So there's sort of an ink reservoir, and then there's this very fine needle, which is about as wide as a human hair. Material is pushed out. In this case, you may be able to sort of imagine or visualize what it's printing. Looks a bit like a butterfly. I don't think the video will work again. No. But then what you're seeing, what's sort of a main, what's important about this material, sort of the main clue here, is that as we're printing, initially when the material comes out, there is no color, and you see it's like transparent, it's a bit, here it's a bit white, and then here, yeah, you have to assume for me that it is green, as it is on the side over there, which further indicates that it's not color that's caused by a pigment, but it's color that's caused by some transition in the material. So as it comes out, it's, let's say, uncolored, and then over time the color forms. This means two things. One, that our liquid crystals work, and secondly, that the printing process also works. I mean, that's also something we should not forgo too quickly. Because in this project, it was really about making the chemistry work, but then also getting the processing just right. So there, if you look along this path, what you do see is this transition, color forming over time, which indicates that we optimized it pretty well. So this is the initial example that we printed, a very brightly colored butterfly, and this was a couple of years ago already. So this was actually the first, well, worldwide, the first printed ink based on liquid crystals. I mean, I cannot add all these caveats, but it was in some way a world's first that we made this, that we made both the ink and that we got the printing settings right as well. And this was all based on the liquid crystals originally developed at Philips. So there's like sort of a very long pedigree of Eindhoven that's, well, sort of encapsulated in the molecules inside this print. However, if you're following this story, you might realize that this one, I haven't said anything about this fourth dimension yet. I've shown you how beautiful it is and how nicely it prints, but it's not exactly sort of four-dimensional yet. So we had to rethink. How do we go from this, which is sort of a good starting point, how do we get it four-dimensional? Well, we go back to chemistry again, we go back into the lab, but there was one problem there, and that's that our magic molecule, they Carrolled open, so the molecule that turns the liquid crystals from colorless to colored. The specific one that we were using didn't really play all that well with the reaction we were using. So we had to rethink. How can we make the material we need with the molecules we need? Luckily, as I said, I think in molecules, I'm a chemist, so I went back to sort of the sheet of molecules I had and started looking for what I was needing. And if you sort of look at it quite abstract, molecules are like Lego blocks. You can take things off, you can put things on there. And with a group of colleagues, we realized that there was one specific part of this molecule that was not playing nice. So what do you do then? You deconstruct the molecule, you take out the part you don't want, and you put it back together again. But more easily said than done, you might imagine. What it actually looks like is something like this. So what I'm doing here, I made the molecule in a separate step, but typically when you do chemistry, you don't only make just the thing you need, but you make a whole lot more. So you have to separate this out. That's what I'm doing here. This is a process that in my case took about 7 hours. It's quite dreadful, but then at the end when you do get the material or the molecule out that you need, and you see it working, I mean that's all the more reason for joy. So at this point we have sort of a concept of the ink we need. We now hopefully have a molecule that works, like this magic molecule. We have a new Carrolled opened that can make it work. And we go back to the synthesis. And this time, all the molecules play along nicely. Everything's happy. Well, especially me. I was very happy with that. And then during the research, so we have our ink now, let's say our 4-dimensional ink, but we don't know if it works yet. I mentioned the printing process needs a bit of work. It needs to be optimized. We don't print butterflies every time. That would take very long. That would spill a lot of material that we could use for more experiments. So we typically print these small strips, quite mundane shape, but okay, it's research. In this case, we chose to make it green again, because it's, well, looking back at this beetle, right? The beetle was also green originally, so that was a logical first step to us. And then we start modifying this, seeing how we can get the best color out. And most importantly, is it actually 4-dimensional? 4-dimensional. Yes, it is. So that's sort of the prowess of chemistry. We had a molecule that didn't work. We designed a new molecule that should work. And alas, it does indeed work. So now we have a green material that we printed. And then after optimization, we can well, sort of evoke a color change from green to, in this case, a bit orange red. This is driven by, and I'll try to keep it clear, the material swelling with water. It's a bit like a sponge if you look at the molecular level. The green strip, when it touches water, it absorbs it, it swells, and remember, because the color comes from a structure, if the structure changes, then also the color changes. So that's how the color changes are caused.
Is also the case with the beetle also?
Yeah, exactly. Yeah, very sharp eye. But it's clear that also in nature it works via the same principle. So it has this, well, some nanostructure.
So a question of swelling.
Yes. Yeah, exactly. And then of course when it dries out, we get the reverse process. Water is released, the structure collapses back into the green state. Now, since we're 3D printing, it doesn't have to be these strips, and I thought printing a butterfly again was a bit corny at this point. So that's where this beetle then came out. This is not a video, by the way, so don't expect any color changes. But you can see, if you look in closely, this one just came from a bath of water. You see some green areas, some more orange areas as they dry out at different rates, clearly indicating the color changing of this beetle. But again, if we're 3D printing, it doesn't also have to be a beetle, it can be something else again. And this is where I try to sort of combine both this color changing sort of beetle concept, the color changing material concept, with the artificial muscle that I showed initially, so this material that contracted. And that's shown here. I think for the video, if someone hits spacebar, maybe then it works. I'm not sure. Because yeah, it's always, PowerPoints and videos are always... Yeah, there we go. So this is the 3D printing process sort of in real time. You can see it's quite slow, but this is how I spent my days on the lab, well, after I got the correcting. And maybe some of you can sort of see what shape it's going to be. I don't really know. It is also nature inspired. Yeah, very well. Yeah, exactly. So this was inspired by a shell, or why a clamshell. I mean, you probably all know oysters with their sort of beautiful lustrous insides. So I was looking for an object or a natural object that had a similar lustrous color as this one. Now this printing took about 45 minutes, so you need some patience, but then it does get rewarded. What then comes out, and I have to see if it loads, is this. Yeah, so don't really look at sort of this weird thing in the middle just yet. But what you see is these sort of two shell-like shapes with this beautiful green color that we at this point know from the ink. But what I did here, I treated this inside, let's say I call it the bridge typically, or this connecting piece. I treated that to be water responsive, and what happens then, and then if you could start the video again, because the clicker is not doing that. As we increase the humidity in the air, this part swells, and that causes the whole thing to fold shut, essentially. Then when the air, you can see it from the moisture as well. When we dry the air out again, the shell opens back up. So in this case, we've combined two properties in a single material. That's both the formation of this like lustrous color, this pearlescent color, as well as sort of a water-driven robot, a very basic robot, which can open and shut this shell. And there it goes again. Yeah, I can look at this over and over again. And then it opens back up again. It's almost alive, I would say. So, so far, that's what I've been working on, is 4D printing devices or objects at a human scale. So I also hope at this point you've got sort of a broad idea of what 4D printing is. So it's 3D printed objects, and that can be the beetles, or it can be the shell that I showed just now, that have a pre-programmed change over time. So that can be a shape change or a color change in the case of the beetle. But at the TU Eindhoven, we not only worked on human scale 4D prints, but also on micro scale 4D prints. That's something that a close colleague of mine worked on. And that is this. It's a very small flower, so this is a microscope image of a very typical human hair. This flower is about as wide, so it's not something that you can really see. Also, once again, I would like to ask for assistance with the video here on the flower. Because what you will then see is my colleague breathing over this flower as he looks at it under the microscope. And you have to look quite closely. Is it playing or not? I'm not sure. But what you will see, I don't think it's going to work. What you will see is this very small flower change color, similar to the beetles, indicating that with our, yeah, I don't think it's going to play. So that means that with our liquid crystal sort of technology, we can print both objects at the human scale, as well as objects at the micro scale. And for both of these, the use might still be a bit far out into the future. But something that you might be able to imagine for this. Ah, there you go. You see a small change. What you might be able to imagine is, for instance, in tissue engineering, so where they try to grow organs, a lot of things get 3D printed, and with this material, they might be able to sort of print sensors on there. So while they're looking under the microscope, they can immediately tell from the color of this flower, in this case, what the conditions of the medium, the growth medium is, or if there's something else wrong. And they don't have to pull out all like big equipment and different probes that they have to then use. So as I said, the future use cases for these materials, they're a bit out in the open, but we do have some ideas. For instance, jewelry. Lots of people wear it, and within sort of scientific spheres, it's always a bit of a weird one to bring up. But clearly, it's important to a lot of people. Just think of engagement rings or pendants that some people wear, sort of a good luck talisman. But what if you could wear jewelry that then also tells you something about your environment? So while the beetle only changes color with water, let's say we give it 10 more years of research and we can make it respond to nitrogen emissions, or we can make it respond to forever chemicals like PFAS. Imagine having a ring around your finger that changes color when it senses danger. Right now that's not possible yet, but that is something that I would love to see in the future. It's definitely going to take a lot more research though. But that's some of the things that might be possible. Another thing that is also being worked on, I mentioned the artificial muscle. This is out of a group of South Korea. So once again, I would need some assistance with the video. And what they're going to show is a small 3D printed hand, again based on these liquid crystals from Eindhoven. That's also humidity responsive. I don't know if it's going to play, otherwise just skip to sort of the middle. It shows a small hand on a stick essentially that picks up this ball and then drops it off on this higher level platform. The advantage of this, because it's 3D printed and it's a soft material, remember the elastic band analogy, the rubber band, maybe it can be used to handle very delicate objects or in surgery where you need to be extremely careful to not harm the patient. If you have what they call the soft robotics, so robotics based on rubbery materials, this can be done. And this is, besides the color changing materials, a different avenue for 4D printing where they can sort of print a device that they need with the specific programmed shape or color change that they need, and then use this, well, for human technology interaction, for instance. Just think of maybe the future robots that they're going to build that we want to interact with. It's not nice if it's like this stiff plastic machine. I always get like these visions of the Terminator, which honestly scare me a little bit. But imagine the Terminator was actually sort of a soft like bubbly robot. I think that would be, well, a lot worse plot-wise, but it would be probably for the better in general. But so there's human technology interaction, but probably also in healthcare, where we're dealing with patients that might already be quite frail, and we don't want to risk their health with sort of these hard metal surgical tools. And then I would like to end off with the future of 4D printing, which is currently in development at the UE. And what you see here is this small strip that also deforms. It's a bit similar to the original one that I showed that contracts with heat. This one doesn't contract with heat, but it contracts with light. So that's what you see here, which is of course a very interesting idea that you can make essentially a piece of plastic, which if you then illuminate, it will change shape. In this case, it can carry a small load. This paperclip, a very small load actually. But what I really like about this one, of course, I think it's intriguing that it changes color with light, or changes shape with light. But to me, the most important thing is that this one is designed from the start to be recyclable. So this one, developed by a good former colleague of mine, he started with the base molecules and started thinking about how we could make those recyclable before even thinking about printing them. And this came out. Clearly, it's very functional. But what's even better is you could cut this small robot or this small strip up into small pieces and then print it again into a different shape. And you could do that a couple of times. And that's where I think the future of 4D printing is, most of all. It's not just looking at different possibilities, but also looking at how we can make it sustainable towards the future. So to recap, what actually is 4D printing now, because I've talked for quite a while, and it might still be a bit puzzling. 4D or 3D printing, that was a technique developed, well, let's say a couple decades ago to quickly transform digital models into physical models. It's worked pretty well for that, but the printed objects are quite static. They're like, well, normal plastic objects. They don't really change, they don't really move. And that is where I feel the future of materials is heading anyway, that we get materials that interact with us in various ways. And this is then where 4D printing comes in. So 4D printing follows from 3D printing in that we design new materials, materials that are responsive, specialized with a specific feature in mind, and they can then serve for a variety of functions. So for instance, sensing, as I mentioned with this personalized jewelry at some point, we can pick up delicate objects, possibly, and then also to help with the quality of life, for instance, in the future, interaction between humans and robots. So with that, I would like to thank you for your attention. If sort of this 4D printing idea sort of finally sort of sunk in and you have some ideas of your own, you can contact Michael, who's also on the back row over there in the grey t-shirt. He's sort of the program leader of this at TU Eindhoven. I've since moved on. I mean, I'd love to get in touch with you still, but I don't work on this project anymore, but you can do so on that email address. And if you want to know even more, if this sort of half hour wasn't enough yet, you can scan the QR code to read my doctoral thesis, which is essentially a book all about this, if you really want to. And with that, thank you so much, and I would love to hear your questions. Yes?
So you showed how chemistry, we can develop a molecule to do some effect. How many times you design a molecule that doesn't work? For example, I guess a lot of it is, in silico, you make something that looks like it's going to do what you want, but is it 100% success rate, or can you talk a bit about that?
Well, it's definitely not a 100% success rate. Well, of course, one of the nice things about, well, I should say academic research is that a lot of it, contrary to industrial research, is published, and well, mostly they only talk about the things that do work, but that still gives a huge body of knowledge that you can sort of feed from. So in my case, the molecule I was needing for my reaction, it did already exist in some Japanese patent. Of course, I couldn't read the patent, but that means it was possibly, well, I could make it in some way. But it just couldn't be built anywhere. So then you try to find ways to make it. In general, the 4D printing concept was really new, so that was a lot of trial and error to get the right material. Because as you might imagine, I mentioned it needs to be this sort of sticky peanut butter type material. Yeah, that's just a lot of trial and error. You make it and then it's too viscous or too thick. Then you try again, it's too runny. And so you try to hone in on the right settings there. For making like specific single molecules, I'm not the greatest expert. I don't work in pharma, so it's not my main business to make molecules, but the ones I had to make were pretty sort of, well, premeditated. We knew they were going to work, and the question was more if I could make them, rather than if the molecules were going to serve their function. Yeah?
I have a question about the time scale and repeatability of, for example, the muscle that you showed that responds to either moist or light. What's the time scale of the contract? Is it very quick or is it slow? And the other question is, how often does it work first? Can you do it 1,000 times? Or?
That's a very good question. That's something that I typically wave over a little bit, this being academic research. The color change in the beetles, theoretically, that should be repeatable sort of, infinitely, because it's not really getting strained all that much. Water goes in and water goes out. For the muscles, they get, the temperature is raised and then cooled down again, and they get heated up again and cooled down. That, of course, can lead to some degradation. I don't think anyone has really looked into sort of when they start breaking. I can imagine for sort of the academic demonstrators, it might be after a couple 100 cycles or 200-300, but don't sort of pin me down on that. For the timescales, that's also a fair point. The original one that I showed that was thermally responsive, that one is quite quick, given that you can heat it up quickly. So if you do it in an oven, it's slow. If you do it with an hairdryer, it can be very fast. Also, the light responsive one at the end, the recyclable one, that was a real-time video. So that one, if you illuminate it, it does contract within a couple seconds. These ones, together with the clamshell that shut and opened, that takes a bit longer because the water, of course, needs to, well, from the atmosphere be drawn into the device. So this one, I think that like a full color change is about 5 to 6 minutes, which, I mean, it's not sort of ungodly long, but it's also not very fast. Then when the atmosphere is replaced with a dry atmosphere, you're of course relying on this water to, well, it's just found, let's say, a nice new home. Now it needs to go out again. So that takes a bit longer, typically about 15 to 20 minutes. So I hope that answers your questions. Yes?
Yeah, you showed that the liquid goes to a very tiny nozzle.
Mm-hmm.
And if you then pressure that crystal to the nozzle, are you not then reorientating those crystals? And if you then make all kind of curvatures, then you have different orientation.
Yes.
Because this looks quite uniform, and
Mhm.
or maybe the nozzle is not small enough. Or did you have problems with that, or did you thought about what that might be doing?
Yeah, well, I should have had you 4 years ago, because that's you're raising a good point. That's typically how they do. So the artificial muscles, so the sort of the things that contract, they were made in exactly that way. So they're relying on this, let's say, this extrusion process to orient the molecules, and then through sort of, well, designing this print direction, they also design, well, the shape change that it gets. In my case, it's a bit of an outlier because I don't want it to be, let's say, this uniaxial orientation, but I need sort of this spiral shape to get the color reflection. And that's also what you were seeing in the video. Well, the video didn't play, but what you were seeing in that image where it was colorless initially and then slowly it became colored. Initially it came out oriented, so there was no color, and then it needs some time and some, well, nudging to form the colored structure. So for most people, this orienting step is sort of critical towards their process. In my case, it was more of a pain in the neck to sort of overcome that.
Yeah. And the other question I have is about that small windmill that you showed, what kind of windmill. The small structure was very tiny, flower.
The flower, yeah.
Did you 3D print it or the etching process? Because I say I cannot imagine that you 3D printed.
No, well, it was 3D printed, but not with an extrusion technique. So that one, well, assuming from your language, you know a little bit about photolithography. But that one was, yeah, I can imagine. That one was made with a sort of micro photolithography, so 2-photon polymerization, if that tells you anything. So essentially, it's sort of like stereolithography, but then at nanometer length scale. Yeah, to keep it sort of understandable, we consider 3D printing to be an umbrella term, essentially. It doesn't have to be extrusion, but it can also be stereolithography. And then this stereolithography can be at very small or very large length scales, depending on, well, what use case we envision. All right, any other questions that might have come up while you still can? Yeah?
I had a question regarding the production, because it's typically quite a slow technique,
Yep.
3D printing, and how would that work in a mass production setting?
Yeah, so that's well, one of the things they will have to look into, and it's I think also something you were thinking about, sort of in the back of your head. Because yeah, 3D printing is quite slow, and that's also why I said in the beginning the conventional 3D printing is sort of in this gray space where it's good for prototyping, but then if you want to scale up, you have to sort of really be able to warrant why you need 3D printing. In our case, we really do need the technique. I showed with the artificial muscles that you need this orientation step of the molecules that make the device. And without this orientation step, you don't have a functional device. So they need to be 3D printed. With these, it might be a little bit less crucial, but the 3D printing does give you a lot of flexibility towards personalization. So with sort of mass production in mind, the mass production I'm thinking of more towards the future is not necessarily to make many of the same devices, but to tailor them to sort of personalized let's say jewelry or pendants or well, devices that are essentially all one-offs. And that 3D printing, of course, is a very valuable technique to have. Yeah?
Another question about are the materials poisonous in any way? Or can you just throw them away? Or do you have to recycle them in a certain way?
Yeah, so that's why I was also so excited about the final example, because that one was sort of made to be recyclable from the start. The material that was used for the beetle is acrylic in nature, so that means that it's a photopolymer. It's sort of this sort of sticky liquid before you print, and then after printing it becomes essentially like rubber. So that's very poorly recyclable, unfortunately. That also does mean that in some way maybe it's more usable in sort of bio settings because it's all fixed inside this polymer. But these, yeah, you cannot really recycle. Once you don't need it, I guess you can burn it or something like that. Very crude, what they typically do. In terms of like actual toxicity or biotoxicity, that's something that wasn't really tested. So right now I can't really say that they're necessarily safe. I mean, it's not that it expels toxic fumes, so it's not like dangerous in that way, but I wouldn't keep it on my skin for too long, just to be sure. So yeah, that's something that still needs to be investigated.
But I can imagine if you design new materials, you have maybe more options to also take recyclability and poisons
Yeah, no, exactly.
into account.
Exactly, and that's, yeah, given the final example. Yeah, I should say that this was sort of a first proof of principle. This was with sort of known material, well, partially known materials, seeing what we could do with those. And then now I pass the baton to sort of a next generation of researchers to see if they can make these applied somewhere. But that's sort of beyond me.
Right. Well, thank you so much for this presentation.
Yeah.
Very exciting prospects for
No problem, thank you.
the future. Thank you all for being here. We are going to have drinks. I think the drinks are definitely ready in the restaurant, but I suggest to go and ask to stay here for a second. I'll go and check with the restaurant if it's okay. They might just come and get the drinks here. And then I will let you know when the dinner starts. It'll be a shared dinner tonight, and Jeroen will also be joining, which is nice. We are here every week, the Innovation Café. If you think this is nice, we'd like to carry this on, maybe you can take a colleague with you or a friend with you next time. That's a lot of fun. Check out the program for the next couple of weeks. And for now, just enjoy the dinner, have a chat with everyone, and if there are any questions, let me know.
Thanks.
Hey, you're still here. So you like the video. If you want, subscribe and click the bell.